Swayam Prabha. Digital India. Educated India.
Good morning everyone. I am very delighted to welcome back Professor Beeraiah Baire for today's continuation of his amazing lecture series on green chemistry. Please join me in warmly welcoming Beeraiah Baire.
Thank you, Amma. So, last, I think Friday or so, last week, we have seen the green chemistry principles, right? How many principles were there? Oh, very good. Okay. So, there are some, each one of them talks about some important aspect of, of the synthesis and the properties of some materials, right? So, we have seen only the principles and what they say. But now, in this class, what we will see is just two examples of how the green chemistry principles have been, can be utilized to address our day-to-day problems. Okay, and it's not only the solving the problems, but helping us also to improve. Okay, our lifestyle. So the two things are the biomass to fuels and commodity chemicals. Another one is plastic upcycling. So if you see the green chemistry principles, so this is the seventh principle, use of renewable feedstocks we have learned. Okay, so if you see what it means is, you have to just, a raw material or feedstock should be renewable rather than depleting whenever technically comes. So it should be like available forever and it should be easily accessible. Okay, and that is one of the main theme of this. So for that we can use the renewable feedstocks. Renewable means it will be there always, like I have explained you that, like particularly the plant materials. So you just every time you can grow. So we wanted to have for everything the source of materials unlimited. Okay, so but how do we get that unlimited materials? It's not easy. So whatever, suppose particularly the plant materials or anything, after one use, you take suppose the sugar cane, you take a juice and the lot of pulp will be there and you will be throwing out. So there is a lot of waste is accumulating, that which we have seen. Okay, so now the idea is there is something edible, that is which we can eat. Okay, but along with that there is a lot of non-edible products also, materials also forming. So the idea of this green chemistry here it is, so can we utilize this non-edible materials, which is so far we call as a waste materials, but now we should not call them as a waste materials. Now they are actually resources for many useful things. So that's what I'm going to show you. Okay, so how this principle actually people are utilizing this guideline or principle into our day-to-day applications. Okay, so what materials can be processed? So there are a lot of materials. If you see, there are waste materials will be there everywhere, the food waste, bio waste, okay, electronic waste, okay, many waste. So what can we utilize actually and what people are doing? So this is all only one type of using. So what type of materials can be utilized or people are using is, you can see that agricultural waste, and we see that in Punjab, or that they make this a lot of wheat and rice, and at the end of the crop, so earlier farmers used to actually decompose the agricultural waste, okay, by doing plowing and watering the this one, and they were never burning that, but it used to take few months, maybe like this summer, April the crop comes, April end of or mid of May, and immediately after the crop, so they plow it and water the land, so and leave it for 1-2 months. By the time the rainy season comes, it will decompose and actually it will be acting can act as a fertilizers also. Okay, so but nowadays we people want everything quick and people are burning the agricultural waste, and that we can see that every time the news comes from the particularly Punjab, because that is affecting the Delhi, because they are burning all the agricultural waste and a lot of smoke and pollution is created, right? So you can actually, instead of burning that kind of agricultural waste also we can use. Okay, why should we burn? So we can reuse. And forestry residues, Food waste. Every day you see that hotels and in many places, lot of food is wasted and they'll be throwing out even at a home also, a small home will be wasting a lot of food, right? So even that food waste also can be used. Animal manure, garden, yard waste, anything, industrial organic waste. So far all these things have been considered as a waste, but now there is no waste. We can always reuse them, but only thing I will show you one example how people are utilizing. It's not that it's the end of that use of these materials. There are many uses industry is using, but I will show you one example only. So before going that, so I just want to show you exactly what is going on. So this slide I have shown you already, that these epoxides come from the bio waste, particularly the triglyceride waste, okay? And this will be reacting. It's a chemical. Don't worry. I told you last class also. Don't try to remember or anything. Just try to understand the very general concept of these things, okay? So because you will not be able to really remember or anything, lot of things. So that's okay. So they will be making this kind of polymeric materials or this kind of small molecules which will be used as a building blocks, or the polymeric materials which will be used for our day-to-day applications. This is one people are already using. Okay, so I'm not going to discuss these details more, but I just want to show you. This is one direction people are using. Okay, they want to synthesize the materials, okay, from a bio waste or any kind of waste, okay, which we are throwing out. Okay, and you can see the few examples. And if you want to consider the actually the what you can say, that motivation for this use of waste materials, okay. So whatever we call a waste or unwanted materials for a useful products, photosynthesis is the ultimate example. What it actually uses? It uses carbon dioxide, which is considered as a toxic gas, okay, poisonous gas. We don't want to have more than a certain level of concentration in our environment, right? But actually photosynthesis uses a carbon dioxide and after all water, and both of them are renewable. Plenty is there, okay. And in addition, this is actually a poisonous gas. So we can, whatever we say that so far our vehicle like a fuel burning, fossil fuel burning is releasing a lot of carbon dioxide, carbon monoxide. Actually, the plants are consuming that. I don't have data actually. There is another slide I missed it. So what it is using is only a sunlight, a chlorophyll, which is a catalyst which comes from the plants, and it makes the glucose a useful gas, oxygen. So photosynthesis, that's why you need to plant more plants. You need to have more and more forests. Okay. So it's not that only the land, but you see that it will be giving the food us, and it is releasing out oxygen, a useful gas. It is consuming the toxic gas. How useful it is, photosynthesis. This is one good example of using a renewable resources for a useful purpose. This which nature does, we are not doing. Which nature does. That's what I last class also told you. You try to mimic with the nature, there are no problems. If you deviate from the nature, everything is a problem. Okay. And this is what we do. We also, what we will take? We are taking sugars, oxygen, useful gas. This is our respiration. When you take oxygen, what happens? There is some chemical reactions happens, right? This was similar, right? And you get release out a lot of carbon dioxide. We are working exactly against to the plants. And our population is increasing, plants population is decreasing, and it's like a double effect actually. You are releasing out, consumption is going down, releasing is more carbon dioxide, and that's where actually is a danger. Just I'm telling you, so this is also a biological reaction, or this is also a renewable resources. Okay, it's not that always this is a useful product. So there's a lot of waste. This comes carbohydrates comes from a lot of waste materials also. So we can even here the main point is not the carbon dioxide generation, but energy release. So we should focus more in that point, not on the carbon dioxide. Okay, that's what we cannot live without breathing. Just by looking at a carbon dioxide, if you start breathing, then you will die. But you should look at the positive side of this reaction. That is the energy release. Okay, that's okay. So now that is what is going on. So people are using a lot of bio waste into some useful materials, which is mostly replacing the what you can say, the plastic materials, other things. But I will show you how the biomass can be used for the fuels. See, currently it's a big problem. Just in the morning I went to the canteen. They say that limited food, not the food actually, limited items due to the gas shortage. I saw, okay, which means they are preparing only limited for 3-4 types of varieties rather than the 20 varieties. That is what the common problem, and now you can see that everyday news, PM also said that you have to save energy, like fuels, all those things. This is all about fossil fuels, which comes from the earth crust, right? But if we can synthesize the similar kind of fossil fuels in a bulk scale and using a bio waste, that would be fantastic. Right? You don't have to depend on the Iran or Arab countries or anybody. We can actually have a plant and we can make our own fuels. These are exactly like your fossil fuels only. Okay. So, but how do we make that? Who will make for us? A chemist can do that. Particularly organic chemist can do that. How? Before that, we should know what is the chemical structure. Last class also I told you, if you start looking at everything in terms of chemical structures as a chemistry, you will understand more and more details. And everything looks very simple. Don't look this as like some object, but there is some chemical entity in it. It is made of some small molecules, right? Similarly, if you know that what is the chemical structure of biomass, whatever we are calling bio waste, whatever it is, what is that? It is after all like some organic compound or some heterocyclic compound, okay, right? Some chemical compound. And fuel is also some chemical compound. So which gas we will use in for cooking? Pardon? What is the chemical structure? I am asking chemical structure. The gas cylinders which your mother carries. So what is the chemical structure of the gas? What is that? C4? Okay, what is that C4? Means what is the name? Butane, isomeric butane. Some little bit of propane also will be there. It's not a pure butane. Okay, you will have that. So now you know that C4 alkane, after all, right? And if you can synthesize the C4 alkane, that is a fuel for your cooking. As simple as that. What is the diesel? A C12 alkane, a mixture of C10 to C12 alkanes, N-alkanes. So, fuels are mostly the hydrocarbons. I will tell you why we should not have the oxygen or hydroatoms. That will come next. So, most of them are the hydrocarbons only. So, once you know that for each fuel, the fossil fuel, whatever it is, right? So, what is the chemical structure? Then if you can synthesize them in your laboratory or in industry, in a bulk, industry means it's a bulk scale. That's all you are making your fuels, fossil fuels, right? What is the problem? Huh? Okay. So this is what we get currently, the fossil fuels. So for your understanding, I will give you just the range of this. So this is very important for you because now we are going to do some chemical reactions from using a bio waste, and we will be aiming for that. And it's not we, actual industry is already doing this. Okay, that's what you see that biofuels everywhere these days, like plants are there and you can fill also. There's a purity things. So now, if you see C1 to C4, that's what your cooking gas. Isomer. So nothing is a pure one. About C5 to C10. This is the regular chemicals. But we are looking at only the fuels, right? And if you see that gasoline, petrol and vehicles, it is a C5 to C10. Another, okay. So this is a C9. So we can use the petrol and other fuels. So since I am a synthetic organic chemist, I will be looking only at everything as like organic molecule. So once I know that, if I can make find a method to synthesize them, whether it is a small molecule is there, I have to stitch them together to get this many number of carbons. If I have a bigger molecule, I have to degrade into a small molecules. There are two ways I can make it, right? So that's what we need to see. So kerosene, C10 to C16. How many of you have seen the kerosene? Have you seen that? Oh, good. Because these days it's not like supplied. And diesels mainly, C14 to C12. sorry, yeah, C20. Just I will stop here. So these are some of the very commonly used fuels, okay, in our daily use. The other things and all we don't use very daily, okay. So, but how do we get that? So before that, this is the structure of a chemical structure of your fuels. But we should know the chemical structure of the bio waste. Then we will see that how do we convert that into this using a chemical things. Any waste you take it. So now there are three major types of chemical entities present in any bio waste. These are now I'm not telling only them. There will be other things, but I am telling these are major structures, chemical structures present. One is starches, which come from a corn, beet, sugar, cane, anything. Similar, few examples. You have a triglycerides. This is a structure which I have shown you last class also, which are very high energy molecules. When you are hydrolyzing them, a lot of energy will be released out, and you see the long chain alkanes will be released. And you see that all these alkanes, they will have sometimes like unsaturation bonds also. And what happens is, if you compare that numbers, it will be exactly matching with this diesel, C14 to C20. All this. There are variations, structures. So if you hydrolyze the triglycerides, actually you get directly the biodiesel. Whatever you now you call as a biodiesel, actually people can get directly from the triglycerides. Simple hydrolysis reaction will give you the biodiesels. Okay, and the source of the triglycerides is main source, some of them. And you see that cellulose, so plenty starch and cellulose is everywhere. Okay. And these are the structures. These are like you can say carbohydrates. These are also carbohydrates. So they can be like sometimes 5 carbon units carbohydrates like hexoses, or they can be a pentoses, 5 carbon units also, or 6 carbon units also. Carbohydrates. 2 types will be there, pentoses and hexoses. So depending on the source, that structure will be there. But now, since all of them are polymeric structures, right? This is also like, you can see that like a triglyceride, you have like a glycerol and 3 carbons like ester linkages. So if you hydrolyze, you will get them. But now what you will do with them? Between them, there is some ether linkage, this is called glyceric bond. It's after like carbon-oxygen bond. This bond, this is either you can call it in simple organic terms, ether bond, or when this particularly, when it is used in the like a carbohydrate, it's called glyceric bond. Okay. So whatever it is, so all we need is we need to cleave this bond, CO bond. And what happens is you get all these small molecular entities, either C6 or C5 units you will get. But the important point here is, if you look at this side, they don't have any heteroatoms. If you hydrolyze, okay, except the carboxylic acid, there is no heteroatoms, right? Mostly the carbon and hydrogen. But if you look at here, there are some oxygens. There are some oxygens. Now, can we use them directly? No fuel should have a heteroatom, CX bonds. The reason, simple reason is, see, when you have a hetero bonds, CX bonds, CN, CO, C halogen bonds, they are reactive bonds. They are very sensitive. Okay, so they can react with anything. They are very sensitive to the light, they are sensitive to the temperature, they are very sensitive to any small chemical impurity also. So, which means you will not have a much control on their burning, and they just blast. That's why the nitrogen derivatives, have you seen, will be used mostly as explosives. Highly nitrogen content based molecules will be used as explosives because they react very rapidly. Similar thing here, if you want to have a controlled release of energy for your fuel, as fuel means, yeah, that's a controlled release, right? You should not have any heteroatoms in the fuel. So it should be purely the carbon-carbon bond or carbon-hydrogen bond. That's why only the hydrocarbons will be a good biofuel, means fuels. Okay. So that's why now, once you look at here, we are just using them and cleaving, but you have an oxygen bond, carbon atom. So what should we do is, we should get rid of these oxygen atoms from these molecules. That is the first thing you are supposed to do when you are trying to make biofuels from a bio waste. You should try to remove the heteroatom content, mostly the oxygen here. You need to remove them. The next, once you are removing, most of the times you will get the polyphenic bonds. Let me write here. Just telling. Suppose you have a OH. Okay. Anything, a cyclic system. So when you are trying to do this heteroatomic oxygens, lot of times we create unsaturation bonds. And even unsaturation is not good. You should not have unsaturation also as a fuels, because carbon-carbon double bond, carbon-carbon triple bond, any unsaturated bond is also reactive bond. Okay. So they also, when I say reactive, see, at the end of the day, you will be burning the chemicals. But the control should be there. But when you have this kind of reactive bonds in your molecules, you don't have much control. Their called sensitivity increases, their sensitivity. So we should get rid of even the double bonds also. You may create, but you have to get rid of the double bonds. So what are the two principles? You need to remove this means you have to do the deoxygenation first thing first, and remove the unsaturation. These two things you have to do. Okay. But even after doing that, you are only getting either 6 carbons or 5 carbon units. And if you look at your fuels, they are only good for your cooking gas, not for all these things, right? So you have a 6 carbon or 5 carbon units, but you need a longer alkanes, N-alkanes. What you can do is, you can design a chemical reaction to stitch them together through a CC bond. They have a CO bond originally. Now you convert into a all carbon-carbon bonds. So the small molecules will be stitched together. And according to your reason, if you want a C12 or C10 unit, accordingly you can choose the building blocks and stitch them together. Okay, if you want the C20, you have this is a major source from the bio waste. You have plenty of it. And you can find out the other small molecules and stitch them together, make all CC bonds. And during that, you need to remove the deoxygenation also, remove the unsaturation also. And by looking at that, you can stitch them together. Or, you see, anyway, you don't have any larger molecules, so mostly it is a stitching together. It's a condensation reactions. Then, removal of oxygen and removal of unsaturation will give you the fuels. This is a very general picture I'm talking about. I'm not showing you any chemical reactions also. Very general principle is this. Converting a biomass into our required fuels. So far, we can call them as biofuels, not a fossil fuels, because they are coming from a bio waste. And people are, industries are already using this and producing lot of biofuels using the similar principle. Okay? Maybe I have a few. Yeah, one interesting point. So by doing this, you guys may not be knowing, there is something called bioethanol. It was in the market few years back, maybe a decade or more than a decade back. Maybe few of the senior people of my age knows. So what happens is, this is what the major bio waste chemical structures. So earlier, people were using, when this idea came to the people, okay, scientists or industry people, they started using first the edible products. That was the origin of biofuels actually. When I say edible, which the food which we eat, not the waste which we throw. Okay, so they were using the food for making ethanol and diesel. Okay, so this is what bioethanol. It was there in the market for a long time and it was discontinued. So it was used as a fuel also, bioethanol. Okay, biofuel. But what is the problem here is, you are actually consuming the edible product which we eat. But if that would have continued, we would have been like a shortage of food. Because we are not using the waste. We are using actually the fuel versus your stomach. A vehicle's tank versus your stomach. Whether you use that useful food to fill your stomach or to fill the vehicle tank. Right? Only one source is same. But you have two uses. So there used to be like if that would have continued, it would have been the same problem, like you have to think every day to fill your tank or you have to fill your stomach. Yeah, there was a nice cartoon. So to start with, it was a nice plan, but it was not a sustainable plan. It was only a quick solution for that point of time, but it could not sustain because it was actually competing with our edible, eatable food, right? So people started thinking, no, this is not going to be a long-term solution for us. So what can we do this? What can we do is there is something called waste which we are throwing. Can we relook into that waste? Okay, that's where the current thing. So everything is a chemical entities only. But now the waste of the whatever the food you eat, you take the remaining waste, agricultural waste, whatever the waste, which will have this kind of chemical structures I have shown you. Waste also has. But initially people thought only this will have. But waste also has the same things, and now people are using this waste into converting into a liquid alkanes. That's what the biofuels we are making. All this list of fuels people are doing. It is in practice. Okay, I'm not telling just on like a textbook example or anything. It's a practically used and people are doing this biofuels. Okay, so now we are using only the waste, not the edible thing, not non-edible things. Now the interesting point here is no competition here. You have always every day plenty of the waste you can get. There is no limit. If you eat 1 kg of edible food, you will create 10 kgs of non-edible waste, right? So there is no problem at all. There is no, now this is no more a waste. You will not call this as any more waste. It's a useful product. Only thing its applications are different. Okay, some point of food from the plants you eat, some remaining thing you will be using for a fuels. That's all. So nothing is going waste now. So this is the principles for now. People are using this one. Just note down, not the top part, the bottom part. That's what that people have to work out. It's not that one day experiment, right? It's a long-term process, and it's always lifetime improvement. There is nothing like called perfect synthetic method or anything. There is always scope for improvement. That's what I'm just going to show you a few methods. Okay, see, we cannot learn or teach you everything, but what you said is correct. So that we have to find out methods which will give us the efficiently the required products. And that's why many scientists, many industries will work. And they have been they have been working, and they are like finding out some interesting catalytic methods, interesting processes to get the efficiency, to increase the efficiency of these processes. Yeah, it's not that like one method somebody reports and that's the end of the day. No. Anyway, so this is what I have shown you all. So what you have to do is you need to reduce oxygen content, make the CC bonds as whatever your requirements, and make sure no unsaturation bonds in the molecules. And this is what one of the very important slide. So you take a cellular or any waste, okay, what you can say, the glucose base or what you can say, sugar based waste. Mostly you convert into the 6 atom unit, okay, 6 carbon unit, and which will be converted. I'm not showing the chemical methods, that will be too much for you people, that's okay. So from these two, so these are the very direct chemicals people synthesize. From cellulose to these are the 3 important molecules people synthesize in industry. First thing, these are like first products, the primary products. From there people use them as like a building blocks, because now this has 6 carbons, this has 5 carbons, this has 5 carbons. Suppose you want to make a biofuels, there are plenty, right? So if I want to make like only the cooking gas, I can take this and do the deoxygenation bulk, I'll get to close to my cooking gas, right? If I want to have a C5 to C10 units, I can take these 2 units of them or another 5 carbon unit, some other molecule, and do some reaction, and finally remove the oxygen, and I get to a C10. It's all about simple chemical reactions. Okay, nothing more than that. So, but these are the primary products from this bio waste. Always a industry makes these are the this as a primary products, because they are easy to get. From there, people again deviate. Okay, use them as a building blocks for a different purposes. And this is called HMF, hydroxymethyl furfural. You will always hear whenever the biomass comes, because this is one of the very primary product, HMF, hydroxymethyl furfural. Where if you start with a hemicellulose, which is a source of pentoses, not the hexoses. So cellulose is a source of hexoses. You guys know, right? Hexoses, pentoses? No? Oh. So hexoses means the 6 carbon sugars. Pentoses means 5 carbon sugars. You see this here. 1, 2, 3, 4, 5. 5 carbon sugars. They differ in the stereochemistry. There are plenty of sugars, why it is. But the main thing is 5 carbons. Here you will have additional carbons. So these are called hexoses. 6 carbon sugars. And that is main source is cellulose. And the pentoses main source is hemicellulose. Remember this. Okay, so if you want to, this will be giving us the 5 carbon units. So that's why this is a hydroxy furfural, methyl furfural. This is a simple furfural. So this extra carbon is missing here. Because that extra carbon, it's not that we are removing, the original itself is now, it was not there. Okay, so the process will be same. And if you use this as your resource, you will get a furfural. So this is not HMF, sorry, it's only furfural. So this is a 6 carbon one. So and this is also a waste, this is also a waste. People are doing a lot of chemical process to make this levulinic acid, gamma valorolactone, GVL. Yeah. Loud. Okay. Yeah. No, same only. They will be coming from this. So they will be coming from this. I will show you a slide, okay? So from here, you will be getting the HMF, and from HMF, you will be preparing them. There, okay? So, but this is a direct conversion. That's what I said. These are the primary products. So like first product, then the next people make this one, then followed by this. And these are because we can make plenty, right? And they will be like used as a building blocks for many, many purposes. I will show you a few reactions. Yeah, somebody was asking what was the reactions, right? A bio waste, a exogenous waste, you take a simple HCl based heating at 180 degrees. These are all the conditions to get the efficiency. Okay, don't worry about this. Different solvents to make them the soluble, because the material will not be soluble. Okay, right? So these are the simple HCl based treatment will give you the hydroxy furfural about 85% yield. Okay, so if you start with this, you will get about 85% yield. 89% conversion means if you take 100 molecules of this, only 89 molecules are reacting, remaining 11 molecules are unreacted under these conditions. That is what called conversion. After a 89 molecule reacted, how much percentage of them are giving the products is 85%. Okay, 85% of 89 is how much? And I will come back. It's about 80%. Which means if you start with 100 molecules of this, 11 molecules will be unreacted, and remaining 89 molecules will be converted into this, but not all of them will give you the HMF, only the about 80 molecules. The remaining will go some again decompose, unwanted reactions, lot of things will happen, right? Yeah.
So, but you're using energy to make these biofuels.
Yes, obviously.
Unless the biofuels are able to fetch that energy capacity.
That's what the use. Otherwise, nobody will invest this. If your investment is larger than your utility, it's of no use, right? So obviously, which means that these are all lesser. So you have to use the energy.
So then the
Yeah,
energy
and you need a manpower, money, everything is you need. But at the end, what you are going to get is much bigger than this. Otherwise, who will do this, right? Academic scale, we can do this reaction because we get money from a government. But industry, it's all complete business, obviously. Right? They have to pay the salaries of every employees, right? So they have to get a profit also. If there is no profit, nobody will do this. So obviously there will be a profit and there is a use. So which means whatever the process you are doing, it is much lesser expensive, okay, compared to the what you are going to get at the end of the day. That is simple, understood. Otherwise nobody does this. Okay. Yeah, there are many reactions. Okay, I will not go. And as I told you, to your answer to your question, not only one condition, there are plenty of conditions. I'm just showing you only 2-3 conditions here. Many different scientists, different industries will use different conditions, different chemicals. So here, earlier people are using only HCl. Now people are using chromium chloride. So that maybe any other thing. It's up to you to design a strategy, but the target is same. Your source is same, your target is same. In between the process, chemical process can be anything. That's up to you. Even it's not that only like it is the end. There is always a scope. I'm telling you, there is no end for it. Okay. And this is what people do using a chemical reaction. See, this is a 6-carbon unit. It has a hydroxy group. It has a aldehyde group. Have you learned about the aldol condensation reactions? Not yet, still. Okay, it's a simple condensation reaction. So there is a ketone and aldehyde, there is a condensation reaction. Okay, so what this is called aldol reaction. So you can do the reaction between this methyl group and this aldehyde, and you can make this kind of thing. So now it is a 6 carbons, and additionally I am adding acetone, which is a 3 carbons. So this is a C9 unit. All I need to do is dehydration, hydrogenation. So first thing I have done the hydrogenation, dehydration which remove the OH group. Okay, dehydration means removal of water. Hydration, rehydration, dehydration. In summer you hear a lot. Dehydration means water is going out, removing water. Rehydration. So this is a dehydration reaction. Then that will give you the double bonds. That's what I told you. This is a dehydration reaction. Minus H2O. And then you will do the hydrogenation reaction. Hydrogenation reaction means just you will add a hydrogen in the different forms and you make a alkane. A carbon-carbon double bond or unsaturated bond will be reduced to the saturated bond. This is called hydrogenation. So using a hydrogen, you are doing this. That's a hydrogenation. If it is a removal of water, it's a dehydration. Okay, names. So then you can get a C9 alkane. That's what I was saying, right? If you need a C9 alkane or C9 mixture, and you can adopt this kind of chemical reaction. Or if you need a C12 alkane, one example is you can use the 2 molecules of same HMF, do the condensation, simple aldol reaction, and follow by again dehydration. Because why we are doing dehydration? We don't want oxygen content in the fuel. And why we are doing the hydrogenation? We don't want the double bonds also. We don't want. We need only a simple N alkanes, completely saturated alkanes, and we can get a C12 alkane. Just one scheme I am just showing you. Okay, chemical reaction, and this is what people are doing in industry also. It's not that I am just writing on a piece of paper or board and just showing you. It's what is happening in the industry. And depending on what you want, you can change your reacting partners here. This is a source which came from bio-waste. We cannot change this. But it's the reacting partners you can change. Accordingly, you can build your required alkane system. Right? And that's how you can make a biofuels. This is one example. Many things. And this is what HMF will be converted into the levulinic acid and gamma valorolactin. There are a lot of chemical reactions. Don't worry. But they will make from HMF only. So biomass to HMF to the levulinic acid, which will give the gamma valorolactam. And each one of them has their own use in the industry. I will not give you, these are a lot of conditions. Yeah. So somebody was asking gamma valorolactam, what is the use? So this is a 5-carbon unit. You can convert into the by removal of decarboxylation. Removal of carbon dioxide is decarboxylation. You can get a 4-carbon units. And if you polymerize them, you can get all these C8 oligomers. And do a simple hydrogenation, you get in this range, C5 to C10. So petrol-based alkanes you get, and you can make a petrol, biopetrol. You understand? And this is one of the method people use. Oligomers is like a monomers means one molecule. Oligomers means more than one. So like a dimer, trimer. If it is a many molecules, you call it as a polymer. Poly indicates a large number. Oligomers is a little lesser number, usually about 10, 12, 15. Okay, you can, if it's a 2 molecules, dimer, 3 molecules, trimer, tetramer. So oligomer means in the mixture of them. You understand? Yeah. So apart from the fuels, where else we can use HMF? So there are, if you go to chemistry lab or industry, you see that in our lab we have about 2,500 chemicals. Different chemicals we have. Small molecules, bigger molecules, tetracycles, solvents, everything. So how do we make them? How industry makes them? There has to be some procedure, some source, right? So the HMF, people use HMF also to make some of those such kind of molecules which we use in our day-to-day life. Okay, for industry or academic purpose, for food grade chemicals, whatever it is. Okay, so this is just a simple chart. Don't try to remember by heart or write or anything. Just try to understand. Okay, because I learned that you don't have like so much chemistry knowledge so far, so don't worry about it. Just listen. Okay, because it's all like a general chemistry. If I teach this to a simple as a pure synthetic organic chemist, which I teach for my MSc students, they will understand each and every step. I have to explain for them, because they understand what is the chemical reaction, what is the mechanism, why that is only forming, why not this one, right? So for you, the idea is converting a bio waste into the biofuels. That is your main goal here. And apart from that, we can make some commodity chemicals which we use daily from the same source, HMF. Okay, there is a lot of charts, and the levulinic acid also you can see. This is the levulinic acid. From this we can make lot of different chemicals which we use every day. Half of them will be there in my lab if you want to go and check it. Okay, so again this is also continuity. So this is about the bio waste to the biofuels. So I will stop it here. You can take a break and we will come back for the plastic upcycling thing. Okay.